we will discuss the various applications of transmission lines. First is transmission lines can be used as circuit elements. So at very high frequencies, the lumped capacitors and inductors cannot be used effectively. That is because at higher frequencies, when we consider inductors, there are some stray capacitance that are developed due to the interturns, and at very high frequency these stray capacitance will behave parallel to the real inductance value, and they will start dominating at very high frequencies, so that can affect the proper inductance of the component that we are using. Similarly, at higher frequencies, if we are considering a capacitor, the metallic leads can cause inductance at very high frequencies, and inductance value will increase for very high frequencies. So because of these reasons, lumped capacitors or inductors are not that effective for operating at very high frequencies. So transmission lines can be used as inductors and capacitors. So we will discuss that. First, let's consider a short circuited line. We know that the input impedance value is Zn is equal to Z0 into ZL plus J Z0 tan beta L divided by Z0 plus J ZL tan beta L. You know this. So when we consider a short circuited line, what will happen? ZL is equal to 0. So ZSC can be written as Z0 into JZ0 tan beta L divided by, this term will be cancelled, so it will be Z0. So you will get like ZSC is J Z0 tan beta L. And if we take beta L as small, you can approximate tan beta L almost equal to beta L. Then what will happen? This ZSC, this is completely, it can be written as JX because it is pure reactance. There is no resistive part because there is no real part. So it is pure reactance, and that can be written as Jx. So from this you can write X is equal to Z0 tan beta L. This is the reactance value. This is the reactance value, and resistive part is 0 because it has only imaginary part. And when for small angles you can assume tan beta L as beta L. So X is equal to Z0 into beta L. And we know that when we take a lossless case, if we consider a lossless case, Z0 is equal to, both R and G will be 0. So it will be square root of L by C, and beta will be omega square root of LC. On substituting these two values in X, you get XSC corresponding to the short circuit value. XSC is equal to square root of L by C into omega square root of LC. This can be written as omega, and here it is beta L is there. So here X will be Z0 beta into L is there. L into beta. This part is beta. Okay. So you can write it as omega L into L. Okay. So ZSC can be written as J into XSC. This will be equal to J omega L into L. So here this is acting as an inductor. This short circuited line is acting as an inductor with inductance value L into L. We know that L is the inductance value per unit length. So L into L is the total inductance value into, where L is length of the transmission line and capital N is inductance value per unit length. So this is from this we can prove that a short circuited transmission line can be considered as an inductor with inductance value capital L into L. And taking this same case, we got the equation as Z SC is equal to J Z naught tan beta. This was the equation corresponding to short circuited line. And here you get X as Jx is this value. So from Z to right X you remove J, because Z is equal to Jx. Okay, so X value is obtained as this. X is Z naught tan beta L. We were writing it in the last step also. So X by Z naught is equal to tan beta L, and tan inverse X by Z naught is equal to beta L. Beta L is equal to tan inverse X by Z naught, and what we need is L. L is equal to 1 by beta tan inverse X by Z naught. Okay, and this is the equation for length of transmission line. So we can write for realizing a reactance value of X. For realizing a reactance value of X, the required of short circuited transmission line is given by LSC is equal to 1 by beta into tan inverse X by Z naught. Okay, so thus we can realize a short circuited line as inductor. Okay, with inductance value J omega L into L. Okay, so this is our first result. Next, let's move on to open circuited line. Again, you know the equation for input impedance. Zn is equal to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. And in case of open circuited line, ZL is equal to infinity, so you are dividing throughout with ZL, you get Z0 into 1 plus J Z0 by ZL into tan beta L divided by Z0 by ZL plus J tan beta L. So here both these will be 0, as 1 by ZL is 1 by infinity is 0. So ZOC can be written as Z0 by J tan beta L. Okay, we'll get like this. ZOC is equal to Z0 divided by J tan beta L. Again, we are approximating tan beta L almost equal to beta L in case of small angles. If that be the case, you can write ZOC is equal to Z0 by J into beta L. Again, you are substituting, assuming lossless case, square root of L by C divided by J. Beta can be written as omega square root of LC into L. So, on substituting, you will get it as 1 by J square root of L will get cancelled, J omega square root of C into square root of C, that is capital C into L. Okay, this can be written as 1 by J omega CL. Okay, so here this is again equivalent to XC. It can be written as capacitive reactance with XC is equal to 1 by omega C into L. Capacitance value per unit length, that is C, L is total length. So open circuited line is equivalent to capacitor with capacitance value or capacitive reactance value is equal to 1 by omega C into L. Okay. So this is another result. So we can understand short circuited line will act as an inductor and open circuited line will act as capacitor. Okay. Again moving on, Z0C, you got the equation as Z0 by J tan beta L. We got this. Multiplying numerator and denominator with J, you get J Z0 divided by J into J, that is J square, that is minus 1 tan beta L. So what will happen? Minus J Z0 cot beta L. Then what will happen? It will be Z OC, that is equal to J into X. So X will be equal to minus Z0 cot beta L by removing J value. Okay, X is the reactance value. Z, hope you know the difference between X and Z. Z is the impedance value. Z is equal to R plus JX. This is impedance value. Impedance value is equal to resistive value, resistance value, the real part. Okay, this is the resistance part and this is the reactance part. It can be either XL or XC, inductive reactance or capacitive reactance. So here you got like this X. So X by Z0 minus X by Z0 is equal to cot beta L, and L is equal to 1 by beta cot inverse minus X by Z0. So this is another equation. L is equal to 1 by beta cot inverse minus X by Z0. This is the length of this. L is the length of open circuited line, the length of open circuited line for realizing the reactance value of X. So this is how we equate the transmission lines to circuit elements. Short circuited line can be considered equivalent to an inductor with inductance value L into L, and open circuited line can be converted or can be considered as a capacitance value with the capacitor with capacitance value C into L. In both cases, L and C are inductors and capacitor values per unit length. So you have to multiply with the corresponding length of the transmission line. So with these equations, we can obtain the required value of reactance by adjusting the length of the transmission line, and based on inductance and capacitor you can decide whether the line has to be short circuited or open circuited. So the topic we now covered is how to utilize transmission lines as circuit elements, inductor or capacitor. Next topic is quarter wave transformer. So we are discussing the applications of transmission lines. So first was to utilize it as circuit elements L or C. Next is quarter wave transformer. Okay, quarter wave transformer means we are using transmission line of length L is equal to lambda by 4. Hence the name quarter wave. L is equal to lambda by 4. And when a load is mismatched, this is general case. If we consider a transmission line, when the load is mismatched, what will happen? ZL will not be equal to the characteristic impedance. So when the input and output impedance are not matching, there will be reflected wave, because we know that reflection coefficient, the equation is ZL minus Z0 divided by ZL plus Z0. So what will happen when these are different? Then there will be reflection. Reflection means there will be loss. For maximum power transfer, for no loss or for maximum power transfer, reflection coefficient should be 0. For that, ZL should be equal to Z0. So what is our requirement? We need reflection coefficient to be 0, and for that ZL should be equal to Z0. Standing wave ratio will be 1. So this is the matching condition. This can be done using quarter wave transformer. So we will check that. How impedance matching is possible with quarter wave transformer. So this application tells that quarter wave transformer, which is quarter wave transformer, that is transmission line with length L is equal to lambda by 4. So how this is used for impedance matching? Okay, so quarter wave transformer again, L is equal to lambda by 4. So Zn is equal to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. And we know that L is lambda by 4. So beta L will be equal to 2 pi by lambda into lambda by 4. It will be pi by 2. And you know that tan beta L, tan 90, that will be almost equal to tan 90. It's almost equal to infinity. So what we are doing is Z0 into, we are dividing with tan beta L. So what will happen? It will be J Z0 divided by J into ZL. So this will be Z0 square divided by ZL. So you get Zn is equal to Z0 square divided by ZL, or Z0 is equal to square root of Zn into ZL. Okay, so this is how we relate the impedance values: load impedance, characteristic impedance of the line, and characteristic impedance of the quarter wave transformer. So that was just the proof. Now let's learn how it works. A mismatched load ZL can be properly matched to a line with characteristic impedance Z0. So this is the real transmission line. That this is the transmission line with characteristic impedance Z0, and this we can write it as ZL. So this is the load. So here there is no match, right? It is Z0 and here it is ZL. So Z0 not equal to ZL. For the matching, you can add an additional transmission line of length lambda by 4. L is equal to lambda by 4. This is quarter wave transformer. Quarter wave transformer, and its impedance, here I wrote it as Z0 dash. So Z0 dash is given by square root of Z0 into ZL. Okay, so you have to take a transmission line of Z0 dash impedance and length L is lambda by 4, and by this you can match the impedance, or there will be maximum transfer of power due to impedance matching. So let's do this problem. We are asked to find the characteristic impedance of a quarter wave transformer needed to match a 75 ohm line. So Z0, the characteristic impedance of the transmission line is given by 75 ohm. Okay, and load value ZL is given by 120 ohm. You are asked to calculate the characteristic impedance of quarter wave transformer. You can write it as Z0 dash, that is equal to Z0 into ZL. To get the characteristic impedance of quarter wave transformer, characteristic impedance of quarter wave transformer, the equation is this. This is the square root of Z0 into ZL, where Z0 is the characteristic impedance of the transmission line and ZL is the load impedance. So it will be square root of 120 into 75. You will get it as 94.87 ohm. Now let's consider half wave transformer. So just like quarter wave transformer, the application was for impedance matching. Here you take L is lambda by 2. Lambda L is equal to lambda by 2 means beta L will be 2 pi by lambda into lambda by 2, which will be pi. So tan pi, you know that it is tan pi or tan n pi, that will be equal to 0. So again substituting in the equation, Zn is equal to Z0 into ZL plus J Z0 tan beta. Thus term will be reduced to 0 divided by Z0 plus Again JZL tan BetaL, that will be reduced to 0. So it will be Z0 into ZL divided by Z0. So here you find that Zin is equal to ZL. That means when you apply a half-wave transformer, there is no change in the impedance. So you can just extend the length of transmission line by adding half-wave transformer, or for if you need no change in the impedance, you can add transmission line of length L is equal to lambda by 2. So you can write a half-wave transmission line half-wave transformer transfers the load impedance to the input terminals without any change. So this is the proof. So the application is different in quarter wave transformer. When L is lambda by 4, quarter wave transformer, it is used for impedance matching, right? Impedance matching. And when we add a quarter wave transformer, then Z1 dash is equal to square root of Z0 into ZL. So you have to take the length as lambda by 4 and the corresponding impedance value should be square root of Z0 into ZL, where ZL is load impedance and Z0 is characteristic impedance of the transmission line. In case of half-wave transformer, you can just extend the distance or the length by adding transmission line of length lambda by 2. Here we proved that there won't be any change in the impedance. So you can transverse the load impedance to the input terminal without any change if we add length in multiples of lambda by 2 or multiples of lambda by 2. So these are the various applications of transmission line.